Alright, so let's start because we have a lot of information to go over. So our problem sets up with a piston filled with an ideal gas. It's placed on a warm brick, so that means constant temperature, and the gas warms up meaning that the volume increases by a small amount of V plus the change in V, as you can see right here. It gives us this equation, which is the first law of thermodynamics, and it just wants us to find how much heat that goes into the gas in terms of little q, V, the change in V, and the temperature. So we know that T is constant. So when T is constant, E thermal equals 0. We know that the V total is equal to the initial volume plus the change in volume. And we know the equation that it gives us, which is the first law of thermodynamics. So we know that E thermal equals 0, so we set that to 0. And since we're trying to find the heat that goes into the gas, we isolate Q, and we get Q equals negative W. And we can calculate negative W as negative nRT ln final volume divided by initial volume. I could show you how we get that right here. So first thing I want to point out is here's our ideal gas equation, which is PV equals nRT. And we're going to need this P later to plug into here. So we just isolate the P, and we get P equals nRT divided by V. So to calculate work is negative, and then our integral of P dV, which is pressure and volume. So the reason why it's negative is because there is less, we can kind of think about it as since there is volume increasing, there is less work being done to push that volume and keep it at its normal state. So now we have our P. When we can plug in our P to here, and we get nRT divided by V. But since we know that nRT are all constants, and we're just trying to find this in terms of V, we can move the nRT to the outside and just have this integral right here. And we know that 1 over whatever variable we're using, I used V. I know it's a little bit confusing. I probably should have used a different letter. When you have 1 over V, the integral of it, it's just log, or ln in this case, of whatever variable we're using. And since we just plug in our integral, so now we have just ln Vf minus ln Vi, which is final volume and initial volume. And then don't forget that front part with all the constants we have to multiply it to. So now we have this, and we can use a logarithm rule, which is log x minus log y. We know that we can just combine that into log x divided by y, and that's what I did right here with our V final divided by V initial. And don't forget our constants we have to multiply in the beginning as well. So that's how I got the work on the gas. So now that we have that, we just plug that into here. And don't forget that there's 2 negatives happening, so that just makes a positive. And then we have small q equals nRT ln V final divided by V initial. Keep in mind that N is the number of moles, R is the gas constant, and T is the temperature. So as for the next part, it wants us to know that this fancy N is equal to the number of moles multiplied by Avogadro's number, and then that Avogadro's number is this number right here. And then it also wants us to know that the number of microstates is proportional to the volume to the fancy n power, and it wants us to know why does it scale like volume to the fancy n power. It gives us a hint of each particle now has more volume to explore. So I can explain this in just how that hint gives us is that if let's just start with a small amount of spots to deal with and a small amount of particles. So if we have 2 spots and 2 particles, we have only these amount of combinations we could have where there can only be these types of states that the particles can be in. And if we add another spot, so now we have 3 spots with 2 particles, it gives us even more different states or combinations that we can have those particles be in. And when you add more spots, it becomes exponential. So like there's a bunch of different more combinations you can have to to get states that those particles can be in. So as for our last part, I'm going to show you how we get this. So it wants us to use the proportionality constant that we used in 3, which is just that n, the number of microstates, is proportional to v to the power of fancy n. And what we can use for this is that when we have our beginning, which is log, I'm going to use ln in this case. They're just interchangeable. They mean the same thing in the case that Professor Tornado is using. Ln of n final divided by n initial, we know that n is proportional to v to the power of fancy n. So that's what I did right here, which is v final to the power of fancy n and v initial to the power of fancy n. And since they're both to the power of fancy n, we can take that to the outside, which is what I did right here. And then there's a logarithm rule that you can move that n to the front and just multiply it by the whole logarithm. And we know that this logarithm right here is equal to q divided by nRT. I could show you that right here because this is our equation from 1.1. And when you isolate ln of v final divided by v initial, you get q divided by nRT. So that's what we have right here. And then we know that this number of microstates is equal to number of moles multiplied by Avogadro's number multiplied by whatever we got from 1.1. We can see here that there are n's on both sides, so we could cancel those out. And then that just leaves us with na divided by r, and then qt multiplied by q divided by t. And we could separate those because we know that this is Mr. B, I can't see his name, Mr. B's number, which is kb is equal to the gas constant divided by Avogadro's number. And it's 1 over kb because this fraction is inversed right here. Instead of gas constant divided by Avogadro, it's Avogadro's divided by gas constant. And that gives us 1 over kb multiplied by q over t. And that's the same as this right here.